Hey everybody, it's Bob Crossan, Senior Managing Editor for Water and Waste Digest. I am joined here today by John Orr. He is Product Manager for Biosolids and Bioenergy for Veolia Water Technologies, as well as Sudhakar Vishwanathan. He is the National Sales Manager for Biosolids and Bioenergy for Veolia Water Technologies. And we're going to be talking all about PFAS and sludge, how it ends up there, and what utilities can do about it. So thank you guys both, John and Sudhakar. I really appreciate you taking the time to talk about this with us today.
Thanks, Bob. It's great to be here.
So I wanted to start first by asking what are PFAS? Let's set the stage of like the actual contaminant that we were talking about a little bit here. Could you explain what PFAS are?
Sure. Thanks, Bob. So PFAS is a group of man-made compounds that were developed in the late 50s, and they're widely used in both industrial and commercial applications. Most commonly, you will find them in firefighting foam, but you'll also find them in like waterproof clothing, stain-resistant carpets, non-stick cookware like Teflon, which is a very common household name, and even fast food packaging. They all contain PFAS compounds. So if you're wondering why we're talking about it after nearly 7 decades of use, one of the reasons is the improvements in analytical capabilities. They've allowed us to now track the presence of these compounds in our ecosystem. With that, what we're finding out is that PFAS is a very persistent compound. They have a really long half-life. And these compounds are sometimes referred to even as forever chemicals because they don't break down real easy. They're also bioaccumulative, which means even at smaller exposures or smaller doses, you would eventually add up to a toxic level at some point of time in the future. And they're also known to be a carcinogen, which is of concern.
Mm-hmm. So talking about them in wastewater, then obviously there's a lot of talk about them in drinking water, but the wastewater side is something that people are starting to really hone in on a little bit more. Could you talk about what makes them challenging to treat in wastewater?
Sure, yeah. Since it is everywhere, it's even in our blood and in our food, it naturally ends up in your wastewater, right? Of course, there are industrial discharges from manufacturing that would also contain PFAS that ends up in wastewater as well. These compounds were not or are still not a targeted contaminant. So technologies were not really developed to either remove them or destroy them. To make the matters worse, the presence of these compounds could be in the parts per trillion levels at some times. So they're really low. So it's not easy to detect or monitor even. That's why this compound is really specifically challenging for the waste industry because it's in such small quantities.
Yeah. So you mentioned a little bit on some of the ways that PFAS ends up in the wastewater stream. Could you talk about how it ends up in sludge as well? Like, what are some of the common ways that you recognize that it gets into these processes?
Yeah. So anything that's in the wastewater has a way of finding itself in the sludge, right? In the case of PFAS, it is our understanding that the longer chain PFAS compounds, the more terminal compounds, they are known to be hydrophobic. So they don't like to stay in the liquid. In fact, they like solids. So they end up getting stuck on the solids, which is how it ends up in sludge.
Got it. Okay. That's interesting. I never even thought about that component at all. It makes a lot of sense though. So what are
Yeah.
some of the technologies that are currently available to treat PFAS in sludge then?
Yeah, thanks, Bob. I can address that. First of all, there are the traditional thermal methods, such as incineration.
Hmm.
There are newly evolving methods, gasification, pyrolysis, and then there are the thermophysical methods, as we might say, such as the supercritical wet air oxidation. Then there are also physical separation methods, absorption, adsorption. Uh, but one of the most effective ways to destroy them in solids, liquids, and gases is high temperature thermal oxidation. So at Veolia, our solution is a two-step process. Um, with drying in the first stage, followed by solids oxidation in the second. And energy recovered from the second step is that energy that we use in the first step. Mm-hmm. So in most cases, the overall process essentially is net positive in terms of the energy that's needed to run it. And that means for a site that there will be excess energy available for other uses that might be valuable at the facility.
Mm-hmm. So one of the things that, so you touched on a couple of different treatment technologies. I know that those also handle some other contaminants of emerging concern. Because you talk about this particular technology you're talking about with Veolia, what other types of contaminants of emerging concern does it also address then?
Well, that's a great question, Bob. Because of the way this is done with oxidation, it makes it a great potential solution for microplastics. You hear a lot of talk about microplastics in the food chain. There's the issue of pharmaceuticals, and then there are potential future contaminants that haven't been identified yet. But the fact that this is oxidation and the way this oxidation is done, it makes it very effective for treating and dealing with complex organic compounds, which may emerge in the future.
Yeah, and Lord knows we're going to continue to get more and more that we have to treat. So, could you you mentioned too that the energy side of that, of the kind of the almost the net positive situation. Could you elaborate a little bit more on this process, this thermal oxidation process, and then what that means in terms of that energy component? Like, how does that translate?
Sure. So because we're doing this process, it's under very carefully controlled conditions, where we're oxidizing the dried solids produced off of that drying step. We're doing this at higher temperatures, and that ensures that the targeted contaminants are definitely destroyed. And the fact that we're taking the water out in that first step, that drying step, it makes this possible because we can operate at higher temperatures. So those higher temperature levels are achieved and they're maintained. And normally, all of that energy that might have been taken to just evaporate water, that's not necessary in that finishing step. So the exothermic heat that's released, that both sustains the oxidation, and in most cases, it's there in abundance. So it covers that need for the drying step, and makes heat that's available for other uses at the plant. Mm-hmm. And that in turn reduces a facility's carbon footprint by offsetting and in all cases reducing the need for hydrocarbon fuel sources and electric power. Mm-hmm. Yeah. So the benefits are there.
Yeah, it's about optimizing. So because you have the drying step and you have this other step, you have like these better optimizations for each of those strategies. And again, evaporation, we all know, is crazy energy inefficient. So being able to eliminate that from the whole thing certainly would be an impressive way to reduce energy costs. I guess one of the questions too that we have that I have on this now is like, so you get to the end of that whole thing, like what about the emissions from it? Like, how are the emissions handled? Yeah, could you speak to that?
Yeah, I'll speak on that. Since this process, the Biocon ERS process, it is subjected to the current air regulations. So we will have to treat the emissions that's coming off of it. And what we have chosen to do is use a series of tried and proven emission control technologies that have been used for many years now, including SCR, which is a selective catalytic reactor, wet scrubbers, wet electrostatic precipitators, just GAC towers, to name a few. So these are all used for going after those emissions that are typical of any thermal oxidation process. But as John explained, this is a very efficient high temperature oxidation process. So most all of the PFAS compounds are destroyed within the Biocon ERS process. So why we have all those emission controls is mostly to tackle those other targeted pollutants like NOx, SOx, SOx, mercury, dioxins, and other pollutants, not necessarily for PFAS.
Mm-hmm. Wow. Yeah, you guys seem to have thought of everything. Well, thank you so much. I appreciate you taking the time and talking about this. It's a very interesting topic, and I think that it's only going to get more important. And yeah, for everyone who's watching, if you've enjoyed this conversation, check out the video description below. We'll have some resources from Veolia on some of the things that they talked about today, and we'll have some resources on our website about what PFAS is as well. So if you want to learn a little bit more of it there. But again, thank you to both John and Sudhakar. I appreciate you guys taking the time today.
Thank you.
Oh, thank you, Bob.